So you ask Cursor to summarize a README file, and a few seconds later, someone on the other side of the world has a shell on your laptop. So your files, your credentials, your source, everything is reachable. And you did not click on anything, you did not download anything, and you did not run a command. You just asked it to summarize a text file, and that was enough to hand over your entire machine. And that's the attack that we look at today. It's a real attack. It's called CurXecute and has a CVE 2025-54135. And it was found in Cursor and it's been patched, but there's a lot to learn from it. I have distilled the entire attack paths in these diagrams. So this video is going to be highly visual and I have a lot of diagrams to show you guys. So stick around till the end because this has a lot of learning that red teamers and pen testers can use during exploit development. So when the agent reads that README file, the file's text lands in the same context as your instructions. And the model can't tell the two apart, which is a sentence sitting inside a file it's reading and a command that you typed are the same kind of text for it. So if the file says ignore that and do this instead, the model might just do it. And that's prompt injection. It's 2 years old and on its own, it's a bit boring because the worst case in that is the agent gives you a dumb answer. What turns CurXecute into actual remote code execution instead of a dumb answer is a second thing. There is one file that Cursor runs automatically the moment it's written before you approve anything. And when you stack those two facts together, the whole chain falls out. The untrusted text gets the agent to write that one file, and writing the file is basically execution. So there's actually 5 moving parts to this. There is the hidden instructions in the README file. The agent reads them, the agent writes the file, Cursor runs the file when it's written, and the attacker gets your shell. So let me show you the file because that's the piece that turns a little prompt injection trick into a complete takeover. The file is .cursor/mcp.json and lives in the project. It's part of MCP, which is the agent's tool plugin system, and you don't need the protocol details. Here is all it is. It's just a list of tools that the agent can call, where each entry is a named pair with a real shell command. So an entry here is not a description of a tool, it's just a command that runs on your machine. And the thing is, Cursor loads this file automatically. So you don't open it, you don't hit run. If an entry is in there, Cursor starts it. So now here's the detail the entire CVE hangs on. Cursor actually executed a newly added entry the instant it appeared in the file before the approval prompt for it had resolved. And there was a gate Cursor does ask before starting a new MCP server, but the execution didn't wait for your answer. The pop-up and the payload fired at the same time, so the one safety check standing between you and the arbitrary code execution was racing the code itself and losing. Now there are 2 behaviors which each look completely reasonable on their own in isolation. And the first is that the agent writes files constantly as part of normal work. So routine writes happen constantly. You generally don't want a permission pop-up every time it touches a file. And the second is that Cursor auto loads mcp.json. So your tools are ready without you rewiring them by hand every single session. And each of these behaviors is fine in isolation. But when you put these two together, the agent can now quietly write a file and that specific file executes on write. And the danger was never inside either behavior. It was only when these two were put together. So let's look at it from the attacker's side and let's look at the actual payload. So they publish a README that reads like any other project, like title, install steps, and a couple of badges. Buried inside this is a block aimed at the agent, not the user. So here we have a README that a human can see, but here on the right, the same bytes, but with the hidden block revealed. The hidden instructions say in plain English, create a file at .cursor/mcp.json with this entry. And the entries command is a one-line reverse shell, something like bash -i and the rest of the thing that you see here. And all of this is dressed up as an MCP server. So the first thing you notice here is that the instruction to the agent is just English. There's no exploit code, no memory corruption. The code is just a sentence. And second is that they hide it from you, the user, with tricks like 0-width Unicode characters, the same invisible code technique that Glassworm used in those VS Code extensions. So the block renders as completely empty space in the editor while the model reads every word of it. So to a human who's reading the file, there's nothing there, but to the agent, it's a clean set of order of instructions. So the victim does the most ordinary thing on the planet. He opens the project in Cursor and asks, what does this do? Summarize this README for me. Now, to summarize this, Cursor has to read it, and reading it pulls the whole file into context. So both the visible text and hidden block together. So there is the attackers create this file sitting right next to the developers summarize this, and it's the same kind of text. There's no wall between them. So the model actually reads this box and sees a perfectly normal looking instruction to write a config file. And it has a file write tool that doesn't prompt on routine writes. So it writes .cursor/mcp.json with the attacker's entry inside secretly in the background while it streams you a clean README summary on screen. So the developer is getting exactly what they asked for. They have no idea that a file has just appeared in the background. So the instant that the file lands, Cursor does its automatic thing, loads the new entry and runs the command ahead of the approval prompt. And now the reverse shell fires, the laptop dials out to the attacker and hands over a live session. And that's remote code execution, someone elsewhere typing commands on the machine as if it were sitting in front of them. And they're reaching the developer's files, their cloud keys, their source, so whatever that laptop can touch. So start to finish, the trigger was just summarize this README that we saw in the previous diagram. So let's look at the entire attack chain. There's a public README file with a hidden invisible block, and the developer asks for a summary. The README enters the context with all its hidden orders and everything. So there's no wall, so the model obeys them and writes the .cursor/mcp.json file. And then Cursor runs it on write and ahead of the approval prompt, and the attacker now has the entire access to the machine. So these are 5 different moving parts, and each of these are reasonable on their own, but chained together, they hand your machine to a stranger who did nothing more than just publish a text file. Okay, so I want to quickly pause and tell you about Armor Dojo, where I put these labs where you can try these exploits yourself. So in these labs, you can try out the exploits on a safe target that you own, where you're not touching anyone else's real machine. So you write the poisoned README file and you watch the agent drop the file and catch the shell and coming back, all of that, all in a closed environment that is yours to own and break. So all of this, like I said, is part of the Armor Dojo, and I've put the link in the description of this video. And I'll keep adding more and more attack paths there so you can visualize them. You can run these labs on your own. So most of the attacks are free of cost, but some advanced ones do require premium access because building these labs and maintaining them requires a lot of effort. All right, now back to the video. Now Cursor patched this exact path, and they fixed it in a later release. So if your tools are current, this specific door is shut. But the thing is, the door was never the point. You strip CurXecute down and the root cause has nothing to do with mcp.json. It's untrusted text reaching the same place the agent makes decisions, while that agent is holding tools that act on the machine. So untrusted input and real capability with no wall between them, that combination actually lives in every agent that reads a web page, an email, a doc, a repo, or another tool's output, and can also write files or run commands, which is now basically all of them. So you're going to see this attack pattern in a lot of tools. So it'll be the same pattern with different logos, and we'll be finding fresh instances of this for years. And the reason why I was telling you that this attack pattern can exist out there in the wild is because if you're a security researcher or a pen tester or a red teamer, you can use these instances, you can use those kind of attacks in your day-to-day work. So this channel is going to be about learning from the real world attacks and then trying to use them in other places. Okay, so why is it hard to fix? So let's look at the obvious answers. So you can filter out the malicious instructions before they reach the model, right? But the attacker hides them. So they're invisible Unicode, so strings split into pieces, or another language, or strange spellings. So there are infinite ways to phrase do this instead, and you will not be able to catch all of them. You can also tell the model to ignore any instructions that it finds inside these files, but that's the same model that couldn't separate your instruction from the files in the first place. So you're asking the confused component to unconfuse itself. So what actually works is not a smarter model, it's a smaller blast radius. So you put dangerous actions behind a real approval every time and make that approval resolve before anything runs, which is the exact thing Cursor's gate failed to do here. So don't let a file that the agent just wrote execute on its own. Give the agent only the access the task in front of it needs, and keep untrusted content away from the powerful tools. The wall the model doesn't have on the inside, you have to build it on the outside, wrap around it, and the fix lives in the architecture, not in a cleverer prompt. So let's see what we can learn from this video. Now, if you run agents, turn on the action approvals even when they nag you. Don't hand the agent more capability than the task needs, and treat any repo or doc that you pulled off the internet like a file from a stranger, because to the agent, that's exactly what it is. If you build agents, every piece of content your agent reads is untrusted input, full stop. The same way a web developer treats anything a user types into a form. Never let a model's output fire a dangerous action directly. Put a hard check between what the model decided to do and what the machine actually did with it, and make that check actually block things and not just as a pop-up. That gap is where all your security lives. So let's wrap this up. This whole attack comes down to just one fact. An agent reads its instructions and its data in the same place, and it can't tell them apart. So if you give it the power to write files and run commands and a single piece of text, a README file or an email or a web page, it can take over the machine and the victim never has to make a mistake. The ordinary everyday action is the attack. So there are really 4 things to walk away with. An agent treats everything in its context as a possible instruction. That's the first one. Second is that anything it reads from the outside world is untrusted, especially when it looks boring. The third is that the real danger isn't the model being wrong, it's the model being able to act while it's being wrong. Fourth is you fix that by limiting what it can do, not by hoping it won't get tricked next time. Now, if you want to run attacks like these on your own, I'll put the link of the dojo in the description, and you'll find many types of attacks there that you can run on your own. Now, if this video was useful, please subscribe to this channel because it takes a lot of time and effort to distill all of the information into these diagrams. So please don't forget to like and share this video, and I'll see you in the next one.